Hello everyone, this is Aris. Today let's talk about Green's theorem in the plane. So we will develop a theorem relating an area integral to the line integral around its boundary. So for example, if you have a figure, say like this, on an xy coordinate system, this region, let's call it area A, so this part here, and the contour or the curve is called C. So what we do, we can first integrate the area of this region A by taking a vertical strip like this at some arbitrary distance or arbitrary position x. So this is x and the y-axis. We start this from a position x equals a to a position x equals b. So there are 2 points here. Let's call it 1 and 2. The leftmost position, the rightmost position. So when we integrate over all area, we'll have two curves here. So this curve at the bottom and this curve at the top. So at the bottom, let's call it lower layer. We can write it as a function y, a function of x. So let's call that yl for the lower layer. So this is a function of x, and at the upper layer or at the upper curve. So let's call it yu. So it's a function, still a function of x. So let me write it correctly. This is supposed to be yl, a function of x, and here at the top it's yu, a function of x. Okay. Also, we can solve the integral by instead of using a vertical strip, we can use a horizontal strip. And then we integrate from the lowest point here, let's call that y equals c, to the highest point y equals d. And we can call this point 3 and point 4. Now between this point 3 and point 4, this region is bounded by this curve on the left, let's call that xl, a function of y, and to the right, let's call that x right or r as a function of y. So we now have these curves here, left and right. So when we evaluate this integral, or double integral here, it would be bounded by this curve xl and xr. So now let us set p and q be continuous functions with continuous first derivatives. We will determine the double integral of partial p with respect to y over the area A. So we write the integral to integrate first the with respect to y and do the y integration. So basically we are doing this. So among these two options that we have, suppose we'll pick this. Okay, we'll do the we do first with respect to y and then do the y integration. So our area integral of partial p xy with respect to y dx dy, we can write it as, so we'll solve dx later, we'll solve y first, and y is partial p xy partial y dy, where y runs from this lower curve to upper curve. And then when we have those values, we can then integrate from x equals a to x equals to b. So this is from a to b, and this is from y lower to y upper. So this can be solved easily using fundamental theorem of calculus. This is simply px at y at the upper limit minus px at the lower limit. Okay, and say we just want to write it in a way so that our path of integration along this curve, it goes counterclockwise. So we go from at the lower curve from A to B, at the upper curve B to A. So basically we're going here and then here. So again, lower curve A to B. So we have negative bx lower curve A to B dx minus, so upper curve u from b to a, so we switch limits of integration, pxyu dx. Now we know that pxyl, yl is the curve, where if you're evaluating that, that is the line integral of p dx along the lower part. And this other one is the line integral of p dx along the upper part from point 2 to point 1. So combining this, we have integral of p dx, but this is from so lower part from 1 to 2, and then upper part from 2 to 1. So basically we're going one full cycle. So by notation, the sum of these two we call integral, closed integral. So we put a circle denoting that it is a closed integral. So p dx, so that the closed path is here we called c. So this is overall c. This is negative of integral. So if you're adding this, we still have a negative here, and that would be equal to this. So negative partial pxy with respect to y dx dy overall area. Now if we integrate first with respect to x on q, so now we'll use q. Respect to x, so we take partial derivative of q with respect to x. This one we take partial derivative of p with respect to y. Dx dy, will do dx first, so we'll put dy here, and dy would be integrated from c to d. So here from c to d. For x, you have x lower and x left and x right. So we're still going counterclockwise. So from left we go d to c, for right we go c to d. Okay. So this would be integral from x left to x right of partial q x y with respect to x dx. And this simply is dy cd, fundamental theorem of calculus. This is q x r y minus q x l y. And after solving this, or after rewriting this so that we specify the path of integration, and then we add that to, you have closed integral along C of Q dy. So we get Green's theorem. So this partial Q respect to x, partial P respect to y, dx dy, that would be equal to P dx plus Q dy taken over all this path. We denote partial C with partial A. Partial A means the boundary of A. So the integral is counterclockwise around the boundary of A. Example, given the force F equals this, find total work done on the closed loop shown. So the closed loop is, so this is x, y axis. Suppose this is 1, 2. So this is 0, 0. It starts from 0, 0, going to 2, 1, along this path, which is a parabola. Okay, so this parabola has an equation x equals 2 squared of y. And then from here, we go here and then down. Okay, we go from this point 0, 1, and then down. So this is the same example we had in the previous lecture. There we calculated the work done along different paths. So this is path 2. This one is path 3 from 0, 0, 0 to 2, 1. Here in this example, you'll find the total work done around the closed loop. So we add this path 2 and the opposite of path 3, or the negative of the work done on path 3. So in the previous lecture, we found the work by evaluating this, but we did only from 0, 0 to 2, 1. So the work done on path 2 is 2/3. The work done on path 3 is 5/3. So counterclockwise around this loop, you have path 2, work done on path 2 minus work done on path 3. So negative or minus here because it's going opposite in direction. So the answer is -1. Now let's try to solve that using Green's theorem. So we have partial, this is Green's theorem, partial Q respect to x, partial P respect to y, take double integral. That's equal to single integral, which is a line integral over the closed loop, P dx plus Q dy. This would be our work done. So work done is the total, the integral over the closed loop of xy dx minus y squared dy. So this xy dx is our p. This here is our p. And this negative y squared is our q. So that our double integral will become partial q with respect to x. So that's x negative y squared respect to x. And the other one is partial p with respect to y. So partial of xy with respect to y. And then dx dy. Okay, so this is 0. So we're left with this partial derivative of xy with respect to y. That's x and negative x dx dy. Now to determine the limits of integration, we can use, we can go back to looking at this figure that we have. So we can do the integration along x first and then y. So for y, it's set from 0 to 1. For x, we can start by using the variable, this variable x, or this function x equals 2 squared of y, x being a variable, a function of, or y being a variable where x is a function of that variable. So we can write it as negative 0 to 1. This is our y. And for our x, you have x starts from 0 to x equals 2 square root of y. So this is x dx dy. So integral of x is x squared. So you have negative y equals 0, y equals 1. So x squared evaluated from 0 to 2 square root of y times dy. So that would be x squared is, this is 2 squared, that's 4 times y, so that's x squared over 2. Okay, so x squared over 2. 2 squared divided by 2, that's 2y dy. And this becomes negative y squared from 0 to 1, so we have negative 1. Okay, so the only difficult part here is knowing the limits of integration. But here, we start from x equals 0, which is this boundary here, and this x equals 2 square root of y. So basically we use the left side and the right side, which bounds the area or horizontally. Okay, so if we use a horizontal strip here, the boundary from the left and right are given by this x equals 0 and x equals 2 square root of y. And we got here the same answer if we use our previous, the results from the previous lecture. By Green's theorem, work done by a force or on a closed path in the xy plane is given by this. If the curl of f is 0, so the z component of the curl would be this expression equal to 0, which is just this. It means that this is 0, so the work around any closed path is 0 for conservative forces, and the work is independent of the path. Now let us define Vx or Q as Vx and P as negative Vy, so such that the vector V is Ivx plus J Vy. And let's consider this figure. So when we try to integrate over all this area of some function, we can make use of this vectors dr, which is the position vector with corresponding components dx and dy. You also have this normal vector nds, normal to this to the vector dr on this position. N is a unit vector. So we have a tangent vector dr and a normal vector pointing out of the area A. So this N here is pointing, so it's tangent, it's normal, but away from the area A. So N is a unit vector, and ds is the magnitude of our dr. So here we can write P dx plus Q dy equals, so our P is negative Vy plus RQ is Vx. Okay. So in terms of this, either of these two, we can have V, we can write it as Vxi plus Vyj dot Vx has a partner dy here, so we can write I dy, you have your negative dx, so j dx. So this is vector v dot unit vector n, okay, or n ds. So from Green's theorem, we have double integral over the area, partial q with respect to x minus partial p with respect to y, dx dy. So that's close integral of partial a p dx plus q dy. So this, or this part here is v dot n. This would be, I forgot to include here, if you, from here, we can determine the value for partial q with respect to x minus partial p with respect to y. So partial q with respect to x would be q is vx minus partial p with respect to y, so negative vy, so it becomes positive partial vy with respect to y, which is just the divergence of v, or you can write it as div v. Okay, so we can use this here. So this is divergence of v dx dy equals, here this is p dx plus q dy, that's v dot n ds. So this is called the divergence theorem. Basically, it's telling us that you have divergence, or if you have an area vector, you can convert it into a line integral, or you have an area integral, convert it to line integral. You have here a divergence of an area integral, it turns into a line integral of v dot n. In 3 dimensions, we can extend this. So we have tau, a volume, partial tau is the closed surface area. So here, the convention in the book, let's just pick, I think this is partial tau. Okay, but I can check this in the book actually. I might want to check this one. Okay. So this is partial tau. Okay. The elements d tau and d sigma mean the volume element and the element of surface area, respectively. Now another case, if we set q as vy and p as vx, and we still have this vector v. As by the way, this is just a specific case. We just set Q and P by some specific values, we choose other specific values here, Vy, Vx. So partial Q respect to X minus partial P respect to Y is this. This is the Z component of the curl of V. So we have here the K hat. If you have P dx plus Q dy, that's I Vx plus J Vy dot I dx plus J dy. So from Green's theorem, you have double integral partial Q with respect to X minus partial P with respect to Y dx dy. So that's close integral partial A P dx plus Q dy. So this becomes del cross or partial Vy over partial X minus partial Vx minus partial Y dx dy. This one is this. So you have I Vx plus J Vy. I dotted with I dx plus J dy. So this is del cross V. Kth component or the Z component. And equal to V, this is V dot dr. Okay, this is called the Stokes theorem, wherein we have a curl of a vector about an area, it turns into a line integral of V dot dr. In 3 dimensions, we can extend this. You have curl of vector over all surface area. It's equal to V dot dr over the bounding curve. Okay, the vector n is a unit normal to the surface.